And then I can read you what this stuff says.
Please.
Is it going?
Yes.
Okay, so this says CACC, calcium activated chloride channel.
Okay.
This says CFTR,
Cystic fibrosis.
Transmembrane
regulator?
regulating something.
There's another word.
Conductance regulator.
Yes, yes.
Cystic fibrosis transmembrane conductance regulator.
Okay.
Cool. NKCC, sodium potassium 2-chloride channel.
Okay. Okay, got you.
It's in the letters.
Okay.
Yeah.
Got you.
And then sodium potassium ATPase
Okay.
for pump, whatever you want. Sodium bicarb channel, NBC,
Okay.
in the tight junction. This is the lumen, and this is like the interstitial space, extracellular fluid, stuff like that.
Okay, got you.
Okay. I'm gonna erase this for a minute. Okay, so this isn't, I'm gonna give you 2 rules that we're gonna follow for this. And if you understand that, the rest of this will make a lot more sense. So the first rule is that 1, sodium chloride is salt and it's readily available to the body. Is that clear so far? You should also know about sodium chloride that it freely dissociates and is not easily permeable to membranes. So, what does that mean? Freely dissociates, that means sodium chloride, when you put it in water, it like gets ripped apart into sodium and into chlorine ions. And your water's gonna wrap around that, and that's Gen Chem, and we don't wanna talk about that, bad times, okay? Not easily permeable means that their ions, they don't cross the membrane of cells at all. So the only way they're getting through is if we have doors to let them, okay? So these 2 properties of sodium chloride, plus the fact that we already have it everywhere, makes it an effective osmol, which is a word that he wants you to know. So if you need 2 things that make an effective osmol, it needs to be something that freely dissociates and that's not permeable to membranes. So the other example he gave is urea. Urea does dissociate pretty well, but it's permeable, so it just kind of goes where it pleases and is not an effective osmol. Your second rule is much simpler than this. Sarah, what is it? It's my favorite rule.
Oh, water follows sodium.
Where sodium goes, water follows. If you learn one thing from physiology, it should be that where sodium goes, water follows. So that will help you with everything else you'll ever do, in my experience.
Pretty much.
Okay. So sodium is our big ticket item. It's like the thing we actually use. But we don't have, how do I explain this? So our cell has to maintain like a gradient, and that means we pump sodium out and we pump potassium in.
Okay.
So we want to end up moving water to our lumen because it needs to be fluid enough so that all the proteins and good stuff in the saliva have some sort of liquid to be dissolved in. There needs to be a suspension. So we need to get sodium from the interstitial space to the lumen. But we can't do that because sodium potassium pump is here and it's keeping sodium out and keeping potassium in to maintain that gradient, which we have to have. Because a cell without a gradient is a dead cell, always, forever. Okay? Sorry. Yes. Oops. Doesn't work. Okay, so how are we going to get sodium to this side when it can't really come in here without just being pumped right back out? Well, we're going to take chloride, because chloride is always with sodium, and we always have it. And it's kind of like the pawn in this situation. So we're going to have a chloride ion, and it's going to go to the sodium-potassium 2-chloride channel. You'll need to know all the specific things I'm getting ready to tell you. It is a secondary active symport. So what does symport mean? That's the easiest.
One direction.
One direction. So it's actually going to be pumping 1 sodium, 1 potassium, and 2 chlorine ions into the cell. And then just to not confuse you, remember this sodium is immediately coming over here and getting pumped out, the sodium potassium ATPase, to maintain our gradient, because that's like the most important thing, okay? And then what does secondary active mean? This is a bit of a reach, yeah.
Where you have to have the gradient to use it, cause primary is the ATPase.
Yes.
And secondary uses the chemical or
Yes.
electrical gradient.
Yes, so it's using the gradient of sodium wanting to get inside because it's at a very low concentration. It's using that to bring the potassium and the chlorine ion in. Does that make sense?
Mm-hmm.
Okay, so now we have chlorine ions in here. It can do one of two things. One, it's going to go through the calcium activated chloride channel, or it's going to go through the cystic fibrosis channel. Hello, we now have chlorine out here. And what you should know about these is that they are, hang on, they're not active, they're passive. They are facilitated diffusion. So what's that mean?
It freely diffuses, but it has to have help.
Yes. So your chlorine is just going to bind to this receptor, there will be a conformational change and it'll go through, but there's no energy required.
I have a question.
Yes.
Is that the apical going into the lumen?
Yeah, sorry. This is apical and this is basolateral. Okay, so are you clear right now on how we're getting chlorine to this side?
Mm-hmm.
Okay. Fun fact, this is a tight junction. Sodium can move across tight junctions. So you have now made this electrical potential across these two spaces. So don't think of what the cell itself is, think of the membrane potential or the potential at the membranes. So like right here and right here on the outside. So you have taken all of these large and charged molecules, these chloride ions, and you have moved them over here. So you have effectively made this space more positive, and you have made this space much more negative. Why is that?
So the ion concentration is different now.
Mm-hmm. And chlorine is an anion, so it's negatively charged. He said he wanted us to know the difference between anions and cations. If it has a minus, it's an anion. If it has a plus, it's a cation.
I was about to say, I would hope everybody would know that.
I just want to cover it.
Through Gen Chem.
Okay. All right, so now we have this very negative space over here in the lumen. So what's going to happen is sodium can cross tight junctions, so it's going to do just that. So now we've got all this sodium here moved into the lumen. And like I said, sodium is our big ticket item, so what's going to follow it is water. Because wherever sodium goes, water goes with it. So plus water, and it can move across the tight junction, or it can go through a specialized channel called an aquaporin, which he abbreviates as AQP. You might see that. So that is how we move water into the lumen of the duct.
Through aquaporins or the tight junction.
Mm-hmm. It can go either way. how do you feel about this so far?
I'm good.
Okay.
So sodium and water can go through the tight junction?
Yes. Okay. Hang on a second. Okay. So you should also know that chlorine moving through the cell is the transcellular pathway. And that sodium moving between the cells is paracellular. Does that sound right? Hang on a second, that doesn't sound right. I don't think that's right.
That sounds right to me,
Does it?
cause para means like next to.
Beside.
The side, and trans means through.
Yeah.
I just wanna make sure.
Yeah, chlorine's transcellular.
Okay,
Mm-hmm.
sorry.
Oh, you're good.
Okay, so chlorine, transcellular, sodium moves paracellular. Okay, next important topic is bicarb, or HCO3, which you'll probably need to know that it means bicarbonate and that it's HCO3 minus. So why do we need bicarb in the fluid of the lumen or the duct cells?
Buffer.
As a buffer.
Yeah.
So what it's going to do is it's going to go through the sodium bicarb channel, which is a secondary active symport. And so it goes with the sodium molecule. So there's this gradient here between there being no sodium in the cell and lots of sodium out here. Sodium wants to get through. So bicarb is gonna ride on sodium's energy to get in through this cell. Does that make sense? Okay. Once you have bicarb within your cell, it's gonna go up here to this anion exchanger where it's gonna bring our chlorine, it's gonna pump it back through, and it's gonna pump bicarb out. Because we have a really high concentration of chlorine out here now, it wants to come back here where there's not very much. Does that make sense? Okay, so that's how we get bicarb through. So it would also be moving transcellularly.
What does that say next to bicarb in the middle?
This?
Yeah, that.
Sodium.
Sodium.
Sorry.
No, you're fine. My eyes aren't very good.
So it goes in with sodium
Mm-hmm.
and it gets out through antiport
Mm-hmm. Mm-hmm.
chloride.
Yes, so that's a secondary active antiport.
Okay.
And then just because I think he might ask, your sodium potassium pump is maintaining the gradient. So you do, what is it, 3 Na out, and you do 2 potassium in. And this is the only primary active antiport.
sodium to 2 potassium?
I can explain it to you, but it's a lot of chemistry. Do you want me to?
Yes.
Okay. That's not a lot of chemistry, just a little. Alright, so we have a periodic table. We have sodium and we have potassium. Sodium has a molecular weight of 11. Potassium has a molecular weight of 19. So sodium is a lot smaller. So we can do 3 sodiums for every 2 potassiums just because of the ratio.
Just because
Yes,
of how big. Okay.
yes, because of the size difference.
Okay.
And that is also why, no, that's not, just stay with that.
Okay.
Does that make sense? Okay.
So what does the primary mean?
So the primary means that you are actively hydrolyzing ATP to make it happen.
Okay.
So an ATP has to bind to the ATPase to move the 3 sodium and 2 potassium.
So because you have to waste an APT every time that happens,
Yes.
that's why you're gonna get as much in and out as you can in each.
Yes.
Okay.
And by doing that, you
Even if it
build,
messes with the charge.
because you want it to be charged. Because this ATPase has built this charge, then you have things that wanna come in, like sodium. So if I put a sodium pump, or if I put a sodium channel here that will let a couple sodiums every now and then come back in, what we want to get in is gonna ride along.
Okay.
So that's why that's secondary, because it took ATP to get here, but it's not directly using ATP.
Okay. Cool.
Okay. So from this, you definitely need to know if they're primary or secondary, if they're antiport, symport. I don't think there's any other options. You definitely need to know what all the letters mean. Oh, one thing. I said that it's more negative here in the lumen and more positive here in the interstitial space. That phenomenon occurring is called the trans-epithelial potential difference, which he abbreviates to TEPD. So he gave some numbers and some math, and it came out that, shockingly, the trans-epithelial potential difference is a negative number, so that it's negative here and positive here.
So basically, all he wants us to know is that it's more negative in the lumen.
And he put on there that you should know how to calculate it. If he asks you to calculate it, you just do one minus the other, and you do whichever is going to give you the negative answer.
Okay.
Because this has to be negative. Like he'll give you the potential at the basolateral membrane and the potential at the apical membrane and ask you to calculate the TEPD, and you just do whichever makes it negative.
Do you remember, the sign or symbol for that? Like if you gave us the equation, we could fill in the actual equation?
I don't remember it, but I
It's
can.
like something in.
It's a VT.
VMB, so basolateral membrane minus VMA, which is apical membrane,
And that equals V.
TEPD.
TEPD.
Yeah. So it's VME?
It's VMB.
For
Oh,
basic
basolateral.
Basal, yeah.
Okay.
Or basolateral.
Yeah, so basolateral minus
Minus
apical.
apical. Yeah. So your positive minus a negative will give you, like this will be negative, this will be positive, but it won't be more positive, so it'll be a negative answer. Let me see what else. And I don't know, like, he basically said, from the way I read it, that it was just gonna be like this, right? Not any of the salivary gland stuff.
Yeah, which I don't believe because he really liked the salivary gland stuff,
Mhm.
so I don't trust him.
Yeah, so I don't really know how to,
If
to
this is
proceed or
always
not
on that
proceed.
paper, cause honestly, I haven't even looked at that paper since at the review, then
Mhm.
this is what I'm knowing. If he asks anything else, granted, we can't pull it up on Echo, but
we have the
We have the
email.
By
email.
Epithelial. Mechanisms responsible for establishing and driving secretion of serous fluid from the extracellular fluid into the lumen, specific transporters, identify their membrane location, identify if transport system is primary active, secondary active, or passive in nature, be comfortable in assigning terms symport and antiport, identify solutes that are anions or cations, know differences between transcellular and paracellular transport, be able to calculate TEPD if given voltage across apical and basalateral membrane, describe voltage dependent diffusion and provide an example, define the term osmol or osmotic concentration, thermodynamic basis for water diffusion across a semi-permeable barrier. He doesn't have anything about salivary glands, other than mechanisms
This.
responsible for establishing driving secretion of serous fluid.
That's vague,
Well,
Yeah, I don't.
yeah.
cause this is what drives the secretion, or the
Mhm.
secretion of
This is the
serous fluid into
mechanism.
the lumen. But does he mean like the nerves that innervate the different salivary glands and where they are?
I think so because I made a note on here that says, hang on a second. Remember which nerves innervate what and where they're located.
We can talk about it real fast, it's not too hard.
No, it's not bad.
Okay, does anybody want a picture of this?
I will take a picture.
Okay.
Send it to me, and then we can stop and restart the video.
the thing about you said transmembrane voltage something. That was
Trans
on that.
epithelial.
Potential difference.
No.
Oh.
You just read it off of that. It was like transmembrane voltage something.
So colorful.
It's very nice. I think I know the one
I
you're talking about.
swear you said it.
I heard it too. I don't remember exactly what it said though.
Voltage dependent diffusion and provide an example.
So voltage dependent diffusion would be what our manipulation of chlorine to get water to freely diffuse.
Okay, so that's all that means?
Yeah,
Okay.
because the cell can play games with chlorine and sodium because they're ions, but water just kind of does its own thing. So we have to manipulate this other stuff to make water do what we want.
Okay,
Move too fast.
gotcha.
There was one about thermodynamics. Can
Yeah,
you read that again?
Thermodynamic basis for water diffusion across a semi-permeable barrier. Capillary membrane, cell membrane type junctions of epithelial. According to difference in osmolality across the semi-permeable barrier.
Did he say capillary beds too?
Mm-hmm.
So that's kind of the same thing as this. If he asks anything specific about capillary beds, it would be like the difference between hydrostatic and osmotic pressure. So hydrostatic pressure is like the pressure of the capillary itself is really high, so it wants to push water out into the lower pressure interstitial space. And the osmotic pressure is like your blood protein, so albumin, and that makes your blood very concentrated, so it wants to pull water back up from the interstitial space.
Okay.
So that's all it could that's all he could ask you on capillaries. I don't think he would waste a question on that.
Okay,
I could be wrong.
I don't know, then it says,
I wouldn't waste a question on
consider
that.
addition of solute regardless of electrical charge or mass of solute lowers potential energy of water molecules. Therefore, side of the membrane with lower concentration of solutes has greater potential energy of average water molecule that drives their migration. Note that 1 millimole of hydrogen, sodium, chloride, calcium, glucose, or albumin each provide 1
Milliosmol or milli equivalent.
Yeah,
So I just put kinetic energy of water molecule lowers once something's dissolved in it. Pure water has a higher kinetic energy and will move to areas of lower kinetic energy. So it wants to move to those molecules, so the
Mhm.
higher osmolality, water
Yeah.
wants to move to it. That's all
oh,
I'm saying.
okay.
So think back long ago and far away to Gen Chem. Water molecules, so H2O molecules are like bouncing around like this
Yeah.
in solution and nothing's stopping them, and there's van der Waals forces and all kinds of things happening, but like there's nothing holding them back.
Yeah.
When you add in sodium chloride, it splits up, and then there's this really strong polar thing, and all these water molecules have to go and like swoosh in around the sodium and around the chloride, and then it's like a bump in the road. And now your energy's not as fast, or there's not as much energy
Okay.
because you have to slow down
Okay,
because you just hit the bump
gotcha.
and lost a tire.
And now you have to walk.
Yeah.
Have your phone back.
Thank you.
That was it.
Okay. I don't know. Do we want to do salivary glands? They're pretty easy,
It's fine.
but we can do them.
Yeah, that's fine with me.
Okay, let me just erase this real fast, and it shouldn't take us too long, so we can just leave him running. Unless you want to stop it, that's fine.
No, it doesn't.
It's weird walking in front of the camera, isn't it?
Yeah, I like it.
Alright, some of this will be a little bit of a review from histology, but your parotid is mucus, serous, or mixed.
Parotid is serous.
Good. And mandibular, mucus, serous, or mixed.
Mucus. Or it's mixed.
It's
isn't it?
mixed.
Yeah, sorry.
And then sublingual
Mucus.
is mucus. Good. And then zygomatic is also mucus. So at rest, mandibular is releasing the most. So this would be like resting saliva, if that's a term. And then parotid is the one that gets released when you're actually eating something, so it's called reflex salivation. And I guess it's the reflex salivation because it has all the proteins and like immunoglobulins and stuff to actually take care of whatever you're eating, whereas mandibular, it has some of that, but it's mostly just like lubricating, I guess. That word works? Okay. What two nerves innervate the salivary glands? What parasympathetically?
Glossopharyngeal.
Mm-hmm. Yep. And one more.
Hypoglossal.
No. Think, what innervates the superficial muscles of the face?
It's like this is a trick.
So your salivary glands are in the same region, so facial will also do some of them. Okay, so this is all, glossopharyngeal and facial are both parasympathetic. So we're again gonna have preganglionic, and then at the very end there'll be a postganglionic. And facial does sublingual and mandibular. And glossopharyngeal does parotid and zygomatic. I don't have a great way to remember that. I'm just drawing it the same every time I draw it.
So, which one's facial? Sorry, 7?
7. Question?
I was gonna say, because those two are more like
Doesn't really make sense.
superficial, but yeah, it's not.
No.
I thought that one was facial, and I was like, easy, those are like the two that you can
Right.
see, and then those two are like, it seems like super backwards.
We can't have it be that easy, Kira, gosh.
Right.
So, I think this is really all we talked about. So your postganglionic nerve is going to release what neurotransmitter? Safe guess. Acetylcholine. What kind of receptor? Guess safely.
Nicotinic or muscarinic?
Muscarinic, because it's parasympathetic.
Mm-hmm.
And is it M1, 2, 3, 4, or 5?
3.
Yeah, always 3. If in doubt. And it's like that for all of these, for the parasympathetic innervation. I don't really know what more could be asked of us.
What in the resting animal, which salivary gland produces a majority of the saliva?
Mandibular.
How much does it produce?
60%?
65.
65, okay.
And then which one takes over while it's eating?
Parotid.
And in the resting animal, how much does the parotid accommodate for?
15.
20.
Okay.
And then when it's eating, it goes up to 50.
Okay.
And that just, those are numbers, and he likes numbers.
He does like numbers,
So-
this is true.
Sadly.
Then there is some sympathetic innervation to the salivary glands. So how do we sympathetically innervate the head? This is kind of a trap, but I think you can get it. Think about eyes. How do you sympathetically innervate the eye? It's kind of a trek through the woods, but okay. So sympathetic comes out thoracolumbar spine. Then it has to come up all those ganglia up the vagosympathetic trunk. Then it synapses on the cranial cervical ganglion and goes to wherever in the face it's actually going. So we have, this is going to be our cranial cervical ganglion. You have some preganglionic fiber here. And then it synapses on the cranial cervical ganglion, and it's going to send postganglionic innervation to all the salivary glands. Does that make sense? And it's
From cranial nerves, from the same cranial nerves,
do what?
so it's sending sympathetic, like,
So think of your spine. Where does the parasympathetic come out of the spine? Or
cranial signal.
so you have you have parasympathetic here, and then you have parasympathetic here. Where does sympathetic come out?
Thoracolumbar.
So that's here. But we still have to have sympathetic innervation in our face. So it's gonna come out, it's gonna travel through some ganglia, so it's gonna travel up the sympathetic trunk, it's gonna go the cervicothoracic and middle cervical ganglia, up the vagosympathetic trunk until it gets to the cranial cervical ganglion, which we're gonna say is right here. It's gonna synapse there, and then postganglionic fibers are gonna come out and then innervate the face. So your sympathetic innervation takes a little road trip.
Yeah, but that's what I'm saying, your post-ganglionic sympathetic fibers synapse with the cranial nerves.
No,
No.
they go directly to the salivary glands.
Okay,
This is the cranial cervical ganglion.
gotcha.
I'm
Okay.
sorry.
No, you're fine. It was
Okay.
just the last two arrows were coming from the cranial
Oh.
nerve, and so I was a
That
little
would be
confused.
confusing, I'm sorry. Yeah, I'm sorry, that makes sense. There, how's that?
Thank you. Thank you for clarifying.
I'm really sorry. Okay, so safe bet, what neurotransmitter is released from sympathetic neurons?
Norepinephrine.
Oh, yeah, no,
Yeah,
I
norepinephrine. And what is its receptor?
Alpha 1 beta adrenergic.
Good.
Yeah.
Eyes are picky.
You do. I don't have any
Beautiful.
candy to throw at you like other.
I'm gonna buy us candy for our tutor session.
I have gum.
You probably have mints or some awful thing.
Hey. I do.
Mints.
So cruel. Okay.
Or some awful thing. Oh, and then one last thing. The parasympathetic causes, like the fluid movement we talked about. And then the sympathetic causes the myoepithelial cells to contract. Do you remember what those are?
Yeah, they squish for secretions.
They do. So our sympathetic is gonna make them squish, so stuff's gonna squish out, and your parasympathetic is going to make like the fluid get into the lumen. How are you?
So sympathetic makes myoepithelial cells
Squish.
squish to pump fluid out,
Mm-hmm.
and sympathetic just makes it move.
Yes.
Or parasympathetic.
Yeah, sorry. You got it. That's all I have.
I feel like I learned so much.
I hope so.
Yeah.
We spend 5 days on these things in class.
Personally,
And I got nothing.
yeah, my problem is that I cannot wade through his crap to focus on what's important. Like, I can't organize it. And so I just freak out. But you organize it very well.
Yeah.
And then it's like, oh!
Yeah.
I
tried. Yeah,
Could've
that's,
got this
and it's
last.
really nice.
I wish he would present it like
That would be lovely.
different. Cause
I
it's not
think
that
that
bad.
my problem
He's not.
is
It's not terrible.
like there's just so many words
Mm-hmm.
and like his pictures, it's just like one thing. That's why like at least on a PowerPoint you can like click. and-
Yeah.
But like his picture's just like
Like all of
everything
it's
is
right
there,
here.
and I'm like, okay, I can't just focus on one thing because they're all there already.
Mm-hmm.
So I don't know.
Yeah. Sorry, I had to stand up.
No, it's okay.
That goes very crazy.
How's your head?